Welcome to COT 3100. Today's topic, we're going to discuss the chapter 1, part 1, which is the logic and proofs. In discrete mathematics, we want to know how we can make in arguments, in mathematical arguments, and how we can be sure that they are correct or they're not correct. And so we need to start understanding some foundations, how we make the statements, mathematical statements, or in arguments, and we can prove it. So this is a foundation to take us to actual logic and how, for example, computer circuits are designed. In this chapter, we are going to look at the propositional logic, which is the language of propositions, applications, and logical equivalences. We're going to look at the predicate logics. We're going to look at the proofs and logical equivalences and all of those. In the section 1, chapter 1, section 1, we're going to look at the propositional logic. In this section, part 1 of the chapter 1, we're going to look at the propositions. What are the propositions? And then we'll look at the connectives, which in this case we're going to look at the negations, conjunctions, disjunctions, implications, contrapositive, inverse and converse, and biconditional and truth tables. You all have seen these concepts in the form of the application. For example, in the course Digital Foundation, we looked at the truth tables, we looked at the negation of a variable, and we looked at most of all these things that we're discussing here are the really basis for those Boolean algebra that we learned in Digital Foundation. And we're going to look at it a little bit more in depth and to understand how we make the statements, mathematical statements that are based on logic and are correct or are not correct, and we want to make sure that we understand the concept behind all of those logic. So we start with proposition. What is a proposition? A proposition is a sentence that declares a fact, that states a fact. A proposition is a declarative sentence that is either true or false. So, for example, we say the moon is made of green cheese. This is a sentence that is telling you some fact. However, that fact may be true or false, but can never be both, right? In a mathematical expressions or in the mathematics or the logic, always we make some declaration or some statements. That statement is going to be true or it's going to be false, never both of them. Another example, Trenton is the capital of New Jersey. Toronto is the capital of Canada. 1 plus 0 is equal 1. 0 plus 0 is equal 2. And in these statements, these are the propositions, because in these propositions, whether they are true or false, this is false, this is true, this is true, this is not true actually, this is true, and this is not true. It's false. So as you see, it is a statement that declares a fact, and then that fact, whether it is true or false. And here are some examples that are not propositions. For example, sit down. I'm not declaring a fact. The sentence is not stating a fact. And what time is it? It's a question. X plus 1 is equal to, we don't know about the x. X plus y is equal to z. We don't know x or y or z. So it is not a declarative statement or sentence that states a fact. So the propositions are a declarative sentence that is either true or false. Constructing propositions, propositional variables, for example, P, Q, or S. The proposition that is always true is denoted by capital T. Remember from Digital Foundation, we always say true or false. T, capital T, and F always stays for false. Compound propositions constructed from logical connectives and other propositions. For example, negations. If 1 is true, the negation of 1 would be what? Would be 0. And then 0 is false. So in other words, if you negate a value which is true, you will get a false. Or if you negate a false, you get a true. Conjunctions, which is really in digital or Boolean algebra, we call them and. Conjunctions, which we show them with this sign, that is this and that. All right? Disjunction, it is the or. This or that. And then we will discuss disjunctions comes in two forms, inclusive or exclusive or. In inclusive or, we say this variable or that variable, or this proposition and that proposition. If either one is true or both are true, the answer is, the truth table answer is true. If neither one is true, then it becomes false. While in exclusive or exclusive disjunction, only one of the propositions or variables have to be true, and the other one has to be false. Then we get the true as a response at the end. If they both are false or they both are true, then the answer for that disjunction of those, meaning that variable or that exclusive or that variable, would be false. And then we have a biconditional and we have an implication. Implication is conditional statements, which we are going to discuss. And biconditional is that there are two conditions in both ways. We will, in a minute, we're going to discuss this. This is the part, the section 1 of the chapter 1. Here's the compound propositions or negations, which we are going to discuss. Negations could be expressed as this in front of the variable or a proposition. We assume a P is a proposition. For example, the earth is round. That's a proposition, right? And we say P is a proposition, meaning in a statement or a sentence that states or declares a fact. And the negative of that one, or negation of that one, will present as this sign in front of it. Or in some authors use a line on top of that proposition. That would be also means exactly the same thing as this one. And the truth table for this one is, if this proposition is true, the negation of that would be false. If the proposition, now proposition is, remember, the proposition is a sentence that declares a fact. So if this proposition is false, then the negation of that would be true. Example, if P denotes the earth is round, the negation P or negative P denotes it is not the case that, always we use this one, it is not the case that the earth is round. Or the more simpler way of saying that, the earth is not round. You just negate the verb here. So, and you have seen this one, the application of this one in the Digital Foundation. But this is where the philosophy behind it, where the logic, the real logic is coming from. Conjunction, which is the, we call them and statement, or and, the conjunction of propositions, P and Q. Now, P is a sentence that declares a fact, and Q is a sentence that declares a fact. And now if we and those two propositions or those two sentences, then we have this truth table. If they both statements are true, then the P and Q is true, or the conjunction of those two are true. If one of them is, if the P is true, Q is false, then F is, the P and Q is false. Because in AND statement, we said this and that both has to be true in order to have a true response, true answer. So P and Q would be true only if both of them are true. And if you notice here, only in this case, we have P and Q true, and T is true. Here is F, here's F and T, F and F, meaning T and F stands for true and false. Then the response is false. Example, P denotes I am at home, right? This is a sentence that declares a fact, and that fact may be true or false, by the way, okay? So when we read this sentence, that sentence that is declaring a fact, that fact, even though we're calling them a fact, but it could be true or it could be false. So, but cannot be both of them. And Q denotes it is raining, right? Then P and Q denotes I am at home and it is raining. We just ANDed them, right? We just ANDed those two. Disjunction, which is the OR, what we call them OR in digital course. The disjunction of propositions, P and Q, is denoted by P or Q and has this truth table. We need to learn these truth tables, of course, but you know some of these truth tables by studying that Boolean algebra. So in these situations, if you look at them, the response P and Q is true if one or both of them are true. And it is only false when both of them are false. So if P is true, Q is true, P and Q is true. P is true, Q is false. This is true because we're saying this is P or Q, right? P is false, Q is T. Their answer is true. And if they both are F, meaning false, then the P or Q is false. Examples. Also, please do not forget, P is not a variable. P stands for a proposition, that which is a sentence that declares a fact. So if P denotes I am at home and Q denotes it is raining, then P or Q denotes I am at home or it is raining. All right? I am at home or it is raining. We just, disjunction of those two would be placing an or in between, and it is raining. You see, we are trying to learn to establish the logic, meaning of the logic, by studying these things. Usually, the problems in the real world, especially in the digital world, is some sentences that declares the fact. And we use those sentences, we convert them into some quantitative numbers, some numbers that we can solve them using some form of mathematics. So first in this course, we are trying to establish those sentences, those logics, and then we convert them into some actions. And most of you have taken Digital Foundation and you have seen the real application of this one. But in this course, we are going a little in depth into the logic behind those Boolean algebra. Connective OR in English. As we discussed, we said the OR is, in English, the way we talk about OR is in both ways, whether it is inclusive or it's exclusive. And exclusive means only one of the propositions have to be true in order to get P exclusive Q to be true. And if they both have the same value in terms of the true or false, if they both are true or both are false, then the exclusive OR of those two propositions would be false. While in inclusive OR, we said if one of them, at least one of these propositions is true, which means both of them could be true, or one of them be true, then if we OR those two propositions, that would be, then the result is true. While in the exclusive OR, as you see, if they both are true, it is false. If both are false, it is false. It is true only when these two propositions have different values. One of them is true, one of them is false. All right? Implication. This is very important part of this that we didn't see that much, this one. And we use this in hardware descriptive languages, which is the basis to designing computer components, such as a processor or the buses or the memories, and we always use this language, this implication. And here it is. It says this is called if P and Q, meaning the proposition P and proposition Q. If we have two propositions, one is P and one is Q, then P, this sign, arrow leaving P towards Q, is a conditional statement or implication which is read as if P then Q, and has this truth table. If P then Q. We'll see some examples and we'll make it clear. For example, here, if P then Q, all right? If P is T and Q is T, then if P then Q is true. If P is true and Q is false, if T then Q, then the value of Q is here, so it is P. If P then Q is false. If P is false and Q is true, if P then Q, then you have P, which is true. If both of them are false, if P then Q, the answer is, the truth table for that is true. This is the only one that is a little bit what they may be confusing, but the rest is very much as you see that it's the value of the Q, T, T, F, F, T, T. Here's the example. If P denotes I am at home, okay, and Q denotes it is raining, then if P then Q denotes if, it's a conditional statement, if I am at home, then it is raining. If then, all right? If then. if you put in front of the proposition P, which is I am at home, then you put the proposition Q, which is it is raining. If I am at home, then it is raining. Now, if P, then Q. P is the hypothesis, antecedent or premise, and Q is the conclusion or consequences. All right? So, let's dig in more into the implication. If P, then Q, there does not need to be any connection between the antecedent or hypothesis or the consequent. The meaning of the P, then Q, depends only on the truth value of P and Q. These implications are perfectly fine, but would not be used in ordinary English. It is really used in what we do in designing logic for the building the computer or artificial intelligence, in the expert systems, in a lot of other applications of the computer science, networking, all of them. For example, let's look over it. If the moon is made of green cheese, then I have more money than Bill Gates. All right? Now, this could be, the moon is made of green cheese could be true. All right? It's a statement. It's a sentence that is declaring a fact, right? Whether it is true or false. And then the next one, the Q, is I have more money than Bill Gates, whether it is true or false. However, it is a proposition, which is a sentence that declaring a fact. If the moon is made of a green cheese, then I am on welfare. It's another sentence that we could look at. If 1 + 1 is equal 3, then your grandma wears combat boots. All right? And these examples come from the book, so don't quote me on that one. I'm not talking about anybody's grandma. One way to view the logical conditional is to think of an obligation or contract. For example, if I am elected, then I will lower taxes. If you get 100% on the final, then you will get an A. If the politician is elected, all right, which means if the first proposition is true and does not lower taxes, the second proposition, Q, is false, taxes, then the voters can say that he or she has broken the campaign pledge. So what is that? That means the taxes were not lowered. Something similar holds for the professor. You may get 100%, but he wouldn't give you that A. So this first proposition could be true. The second proposition could be true or false. And if P then Q, then we will look at that truth table. We will figure out exactly what does that mean? What is the results? All right? That's how we are trying to establish the logic when we are designing anything in computer. So this corresponds to the case where P is true and Q is false, meaning something similar holds for the professors, that student received 100%, made the 100, but professor didn't give him an A. Different ways of expressing P then Q. If P then Q. One way is we say if P then Q, or we could say if PQ, or we say Q unless negation of P, Q if P, and Q whenever P, Q follows from P, P implies Q, P only if Q, Q when P, Q when P, P is sufficient for Q, Q is necessary for P. These are sentences that you read when you study mathematics, basically. they all mean the same thing. They all means these are the different way of expressing if P then Q. So whenever we study any logics or any mathematics or when we are studying computer architecture, we see different types of this. Each person uses a different form of this, but they all mean the same thing, and they all follow the same truth table as we saw here. So if the first proposition is true and the second proposition is true, then if P then Q is true. And if the first one is T, the second one is F, then if then Q is false, and in the other cases are true. Okay? Converse and contrapositive and inverse. If P then Q, we can form new conditional statements. One is the totally converse of this one, which is the Q. If Q then P is the converse of P then Q. And the contrapositive means you negate this one. All right, you negate this one. Negative, you say if negation of Q, then negation of P is the contrapositive of P, Q, and also negation of P, then negation of Q is the inverse of if P then Q. Example, find the converse, inverse, and contrapositive of if raining is a sufficient condition for my not going to town. Solution, if I do not go to town, then it is raining. Converse, right? Inverse, if it is not raining, then I will go to town. Contrapositive, if I go to town, then it is not raining. You see, we took that two propositions that we discussed, and we are then building this by negating one, negating the other one, putting them all together, and we are getting a different conclusions from how do we play with those two propositions. So this is the logic behind those propositions. Biconditional means if P and Q are propositions, meaning they both are a sentence that declares a fact, then we can form the biconditional proposition which reads P if and only if Q. If and only if, in mathematics we sometimes write them IFF. IFF, which means if and only if. If and only if. The biconditional P and only if Q denotes the proposition with this truth table. This is the truth table. If they both are true, then P if and only if Q is true. And if they have different values, P and only if are false. If they both have the same value, is true. This is really, if you pay attention, it is really opposite of the exclusive OR. All right? When we design circuits, these things come very handy when we are designing digital circuits. So if P denotes I am at home and Q denotes it is raining, then P if and only if Q denotes I am at home if and only if it is raining. Some alternative ways to say P if and only if Q is expressed in English. P is necessary and sufficient for Q. This is another way of saying the same thing in English. Or if P, then Q, and conversely. Or, as I said it, which we use them really in explaining mathematics, in the mathematics, P, IFF. IFF means if and only if Q. All right? Truth tables for compound proposition. Construction of a truth table Rows need a row for every possible combination of values for the atomic propositions. Columns need a column for the compound proposition, usually at far right. Need a column for the truth value of each expression that occurs in the compound proposition as it is built up. This includes the atomic propositions. This is exactly the way we are saying it here. It's a little bit more complicated or confusing, but you have set up truth tables in digital value foundations, and you know exactly how it works. P, Q, R, negation R, P or Q, P or Q. Well, this one says if P or Q, then negation R. So we put the values for all of these, for P, Q, and R. TTT, this is like a 111, 110, 101, 100, then 011, 010, 001, and 000. We just put them. Sorry. Negation of R, if R is true, it's F. If R is F, it is true. The same way. P or Q, all right? P or Q, if either one or one of them, at least one of them is true, the answer is true. Only there are two situations that both are false, and we have false. Then what we are saying here, P or Q, if P or Q, then negation R. So we are taking these two values, and we do this one based on the table that I gave you for if P, then Q. So here, your proposition here is the compound proposition P or Q, which we have them here, and the negation R is here. Then based on that truth table, you put the value. All right, if it is P or Q is true, then this is F, we'll have them F. And you keep going on. Equivalent propositions. Two propositions are equivalent if they always have the same truth table. For example, show using a truth table that the biconditional is equivalent to the contrapositive. Well, if you look at them, you see exactly they have the same P and Q. You negate P, you negate Q, then you say if P then Q, and you do this one, and you will see if they have the same truth table, then they are equivalent. If they don't have two propositions, if they are only two propositions are same, only if they have the same truth table values. And if they have the same truth table values, then those two propositions are same. Otherwise, they're not the same. Using a truth table to show non-equivalence. Show using truth tables that neither the converse nor inverse of an implication are not equivalent to the implications. Again, the same way. P, Q, negate P, negate Q. If P, then Q, and then if negation of P, then negation of Q, and then Q, E. And this shows that exactly, you go through the truth table. Okay, you could put instead of true T, you could put 1, and you could, for the F, you could put 0. Then you have the truth table exactly the same way that you had in Digital Foundation, and you could do this truth table. How many rows are there in a truth table with n propositional variables? Well, here it is. If you have 3 variables, A, B, C, how many different ways can we write A, B, C in different values? All right. You remember in Digital Foundation, we said 2 to the power of 3, 8. All right. X, Y, Z, you have 8 of them. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0, you go all the way. If you have 2 variables, A and B, 2 to the power of 2 is 4. You have them 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1. And this is exactly what he's talking about, 2 to the power of n. We will see how to do this In chapter 6, we'll discuss that. Note that this means that with n propositional variables, we can construct 2 to the power of n distinct propositions. Distinct proposition is not equivalent, meaning they don't have. Equivalent means they have the same truth tables, but this doesn't mean they have a same truth table. What's the precedence of logical operators when we are performing them? How do we set them up in the truth table? Always negation comes first, and is second, or is third. Implication, or if then, is next, and then the biconditional is the last one. So, and these are some examples. P or Q, then negation R is equivalent to saying that you do P or Q, I'm sorry, first place, and then you go for the negation. If the intended meaning is P or Q, then negation R, then parentheses must be used. All right. Otherwise, this is the format. All right. I'm going to stop at this point, and we will discuss the application of propositional logic in part 2 of chapter 1. And starting next week, I will start assigning the homeworks. I want everybody to catch up and learn how to use these things and watch these lectures. And then I'm going to start assigning homeworks. And also by next week, I should post your exam times. See you next time.